Okay, so good day again to each and every one of you who are currently watching this video. This will be problem number 4 for our general topic shear and bearing stresses. I have here a structure, more like it's more like a plate that is fastened on this tube here, as you can see right behind our given plate, with a pin at let's say this is point B. That is point B, and also at point A. This one has this some sort of a slot and angled about 45 degrees. And for pin A, nothing much changed from this orientation and position. So the problem wants us to simply solve for the shear stress for both at point A and for point B. So it's a pretty straightforward sample problem. There's nothing much too complicated for this sample, but for this case, since we have this kind of slot angled at 45 degrees, we need to somewhat consider this portion of our free body diagram. So upon solving for that one, and don't forget that the diameter of this pin A and B is 1/2 inch. Okay, so let's try to solve this problem. I'm just gonna give some space for us to solve. Okay, so based on the free body diagram that we have, in order for us to solve this problem, let's try to simplify. Okay, this one is, for example, for pin A, and then measuring 12 inches downward is point B, sorry. It should be pin B or point B. Measuring 12 inches downward, okay, that is pin A. And somewhere 36-inch all the way to the right, that is 200 pounds. Okay. So this portion is 200 pounds. This one is 12 inch. Okay, 12 inch. And this one is 36 inches. And don't forget that the diameter of the pin is equivalent to 1/2 inch. Okay. And don't forget that this one has a slot angled at 45 degrees. Okay, it goes like that. Okay, this one is 45 degrees. Now, in order for us to determine what are the unknowns, let's try to consolidate first. What are the forces for each pin A and B? Okay, so upon doing that, for example, here at the point A, or rather at the pin A, we have a 200-pound force that is being applied to our whole structure 36 inches from this datum line. So it means if this 200 pounds has a perpendicular distance equivalent to 36 inches, it tends to rotate the whole structure clockwise, means to say that this A here is somewhat resisting this 200 pounds. So let's try to assume that the y component of reaction A is going downward. Okay, so this should be A sub y. And since this is a pin, it supports both x and y components. Let's assume that x is going at this direction. So that should be A sub x. And here for pin B, since it is somewhat slotted on this gap, having a 45-degree angle, and this pin also supports the whole structure by being subjected by this 200-pound downward force acting 36-inch from this datum line, or from this reference line. 200 pounds tends to rotate the whole structure clockwise, means to say that if this pin B is somewhat slotted in this gap 45-degree angle, means to say that this pin is compressing against this portion of the wall here. So as you can see from our free body diagram, it means that the force that is counteracting this 200 pounds from this pin B inside this slot 45-degree angle, it should be going at this direction, normal to the surface area of this gap. It means that it should be going at this direction. And if this is the 45-degree angle. Okay? So upon doing that, since this is angle, this is R sub B. This one, let's assume R sub by, or simply the y component, and R sub bx for the horizontal component. Okay, so of course, since we have x and y, there should also be a resultant force, which is R sub a. So now we have the forces interacting with our pins for A and for B. Now what's left is for us to somewhat apply the laws of equilibrium in order for us to solve one of the unknowns. So for this case, let's try to use the summation of moments at point B so that we can cancel out everything at point B and determine the forces that tends to rotate the whole structure. Okay, so let's try it. Just going to give this some space. Okay, summation of moments at point B, so is equals to 0. So any forces at point B will be cancelled out. So we have this AX tends to rotate counterclockwise, so that should be negative. And then the perpendicular distance is 12 inch. Okay, so 12 inch, and we have this 200 pounds clockwise, so positive, plus 200 pounds multiplied by the perpendicular distance equivalent to 36 inch. 36 inch. Solving for a sub x is equals to 200 multiplied by 36 inch divided by 12 inch. So 36 divided 12 is simply 3. 12, 24, 36. So 3 times 200, that is 600. It's equals to 600. The unit is pounds. So means to say we have a positive answer. Our initial assumption is correct that x is going to the right. Okay, so that's for a sub x. And the next one is, let's try to apply the summation of forces at the horizontal axis. Okay, so all of the forces going to the right is positive. Summation of forces at the x axis, we have this a sub x, 600 pounds. Okay, so that should be positive, 600. And we have this for the reaction at B for pin B. Let's get the horizontal component, which is RB sub x, going to the left, so that should be negative. You just need to somewhat get the angle for the x component. So R sub B cosine of 45 degrees because it is adjacent. And solving for R sub B, because there are no more forces acting at the horizontal, so we can just simply solve for R sub B. So R sub B is equals to 600 divided by cosine of 45 degrees. So R sub B is equals to, the answer for that one is 1142.16. 1142.16 pounds. So which means that R sub bx is going to the left. Since we have a positive answer, then our initial assumption is correct. So we managed to solve for the reaction at pin B. And the next one is, let's try to solve for the y component for pin A. So let's just try to use the summation of forces along the vertical axis. So going up, summation of forces at y is equals to 0. So we have negative a sub y And what are those forces acting on the vertical? We have R sub B going up. So that should be positive R sub B sine of 45 degrees, and then 200 going downward. 200 pounds. Solving for A sub Y. So this is just a simple substitution because R sub B is simply 1142.16 pounds sine of 45 degrees. And solving for AY, or rather A sub Y, is 771.87. 771.87 pounds. So since we have a positive answer, means to say that A sub Y going downward for our initial assumption is correct. Okay, so we managed to solve 3 forces, and we can't stop there because we just somewhat need to solve for R sub A. Since we have the x and the y component for R sub A, we can just simply use the Pythagorean theorem. Because we managed to already solve for the reaction at B, pin B is equals to 1142.16 pounds. So all we need to do is to solve for R sub A by applying the Pythagorean theorem, since we have the y component for R sub A and the x component for R sub A. Okay, so let's apply the Pythagorean theorem for R sub A. That is simply the square root of 600 squared plus 771.87 pounds. Then solving for R sub A, the answer for that one is 977.64 pounds. Okay. So this is the important ones, R sub A and R sub B. And obviously, we are not going to stop at that point. Let's try to remove some of these so that we can solve for the shear stresses. Okay, so that we can have some space in order to solve. And this is just a simple problem. And R sub B, I'm just going to write it here. R sub B is equals to, from our solution just recently, that was 1142.16 pounds, and then for R sub A, that is 977.64 pounds. So those are the reactions for both pin A and B. Since we already somewhat managed to solve for the reactions, we can now simply apply the working formula for shear stresses, which is tau is equals to the shear load divided by the cross-sectional area of our pin. So solution, shear stress at pin A is equals to 977.64 pounds divided by the diameter of the pin A and B is 1/2 inch. So pi 0.5 inch squared divided by 4. So shear stress at A is basically equals to approximately 4979.08 psi. So pounds and then square inch psi. So this is the shear stress at A. Then for shear stress B is equals to 1142.16 pounds divided by pi 0.5 inch squared divided by 4. So shear stress at B is approximately equals to 5816.97 psi. So these are the answers for sample problem number 4 or number 5, I'm not sure. So obviously at pin B, is much greater because it is angled. So that's the answer for this problem.